Right, so let's get started, everyone. Hello, welcome to the computer science webinar. This is the fourth and final in our introduction to the Bridge the Gap series. And without any more talking, we'll just dive right into this. So this is the lesson plan for today. We'll be going through a quick introduction about the three tutors and Bridge the Gap. We're going through some housekeeping, which is just that we expect you guys to keep your mics off along with your videos. We'll be going through an introduction of what we will be covering, along with some practice, and at the end we'll be going over a review of key concepts. So, about us. We are a newly established company that we formed in 2024. We're focused on giving you guys a personalized tutoring using adaptive teaching catered to your learning style. So, meet your tutors. There you can see me at the bottom left. Then there's my two colleagues, Samuel and Vishan. We all have a strong academic track record across GCSEs, subject Olympiads, personal projects, and A levels so far. We're passionate about our subjects and giving the best tuition to you. We're all predicted A stars, obviously, for A levels. And this is the Bridge the Gap course. Are you looking for a refresher or are you looking to dive into new content? Well, this is the course for you. If you're looking to gain confidence and be able to contact tutors outside of supervisions, well, this is the course for you as well. And if you are interested, please fill in the interest form. The QR code is right here. Or if you'd like, you can head over to our website and all more information will be on there regarding everything you need to know. So without any more talking, we'll get into this. So the learning objectives for today. What is postfix/RPN? And we'll be covering, what they are and what is infix. We'll be seeing how to convert infix to postfix and vice versa. We'll be seeing what is binary, how to convert denary to binary, and vice versa as well. What is hexadecimal and how to convert denary to hexadecimal. Don't worry, we will also be covering what denary is. So I'm going to give you guys a 10 seconds head start to evaluate these following questions. The BIDMAS triangle is right over there to the left. So let's go through this now. 3 plus 4 multiplied by 5. Well, that's simple. That's just 23. This time, 3 plus 4 multiplied by 5. This will be 35. So now this one. 3 plus 4, 7. Multiplied by 5 take away 2, 3. That'll be 21. 2 multiplied by 7, take away 10, plus 4. Altogether, that makes 8. Now, this next one is a little bit longer, so I will go through this one properly. So, first we need to look out for brackets, which we do have. So, we're going to do 2 plus 2, which is 4, and then write out the rest of the equation, multiplied by 4 plus 3. Then we're looking for indices, no indices, so division, we're going to division next, which is here. So 8 divided by 4 is just simply 2. Take away 5 multiplied by 4 plus 3. Then we're going to do the multiplication. 4 multiplied by 5 is 20. And then 3 plus 20, take away 2, you should get 21. Now, this last one here, 3 minus 4 plus 2. Don't make the mistake of adding first and subtracting. We need to go from left to right. So we need to do subtraction first. 3 take away 4 plus 2 should give us 1. Now, you see this expression at the top here. This is what you'd see in your day-to-day maths. So if you're doing physics, computer science, any type of maths, you'll be seeing this type of expressions. The ones with brackets, the one with indices, etc., etc. This is what we call infix. And you'll see this everywhere. However, this expression at the bottom is not as well known as infixes. And this one here is called postfix. Or in other words, reverse Polish notation. Now, it may look slightly different to how infix does, but trust me, it is the exact same expression. And we'll see that just in a bit. And we'll see also why we use this. So first, we're going to look at how to evaluate reverse Polish notation. So let's start off with this example over here, 4, 5 plus. Now, what does this mean? First of all, what we're going to do, we're going to start at the very left of the expression, and we're going to make our way through the expression up until we find our very first operator. We're then going to apply this operator to the two previous operands. An operand is just a number or value that the operator is being applied to. Now, all we need to do is apply this plus to the two previous operands. In other words, 4 plus 5, which will leave us with 9. So if you scroll down here, and now we're going to do the same thing. We're going to start over here at the left of the expression. We're going to make our way through up until we find the very first operator, and we're going to apply that to the two previous operands. So 9 divided by 3, which is just 3. So now this one is a little bit harder because we've got three numbers, two operators, but nothing changes, is the exact same. Starting at the left, we're going to make our way down to the division, and we're going to apply the division to the two previous operands. We're going to be left with 3. We're going to bring the 5 and plus down, and we're just going to repeat the process. We're going to go up until we find the plus, and apply the plus with 3 and 5, we get left with 8. Now the next one is slightly longer, but exact same thing again. So we're going to start off 4, make our way down to the plus, apply the plus to the 4 and 5, we get 9. Copy down 7 to minus multiplication, and then rinse and repeat. Starting at the very left, we're going to make our way till we get to the minus, but we don't want to apply this to the 9 and 7. Remember how I said you need to apply it to the previous 2? In that case, that'll be 7 and 2. So we're doing 7 and minus 2, which will leave us with 5. And then we're going to copy down the 9, and we're going to copy down the multiplication. And then again, we're going to start at the left. We're going to make our way through until we get to the multiplication and apply that to 9 and 5, and we get 45. Nice and easy. But why do we use it? Well, we need to look at the advantages of postfix over infix. The first thing is that there is no need for an order of precedence of operators. In other words, that's just saying that there's no need for any bidmass. As you saw previously, 3 plus 4 multiplied by 5 and 3 plus 4 multiplied by 5 gives you two very different answers. One gives you 23, one gives you 35. And that's because of the presence of brackets. But if we were to remove the brackets in a more complicated expression, that would be a lot more ambiguous. And that's why if we're using postfix, it gets rid of bidmass and therefore gets rid of the ambiguity. So the second advantage is that postfix expressions can be evaluated by a computer as they are entered. In other words, left to right. That's how they are entered. And this means that postfix expressions can be processed faster than infix expressions. And if you can do something faster rather than a slower way, then why wouldn't you do it? It's just a no-brainer, isn't it? So that's why postfix in computer science is a lot more favored than infix. However, you will see a combination of both as you go through your studies. So now we're going to be looking at converting infix to postfix. Starting at this one over here, 3 plus 2 plus 2 multiplied by 5. So what we're going to do is we're going to start at the right-hand side of this equation, right? So we're going to take any operators that we find, in which case we're going to take this, sorry. Okay, just ignore that. We're going to take this multiplication and we're going to move it outside the bracket over here. Then we're going to move across until we find the next operator, which is the plus over here. And we're going to move this one all the way out over here. You'll see this and why, how this makes sense in a little bit. And we're going to move across again till we find the next operator. And we're going to move this one right outside here. So it will replace this addition here will replace this addition over here. And next, all we do is same with the brackets and everything. We're just going to copy it down, but we're going to move the operators from where they currently are to where they're supposed to be. So we're going to do open bracket, 3. And since the addition is moving away, there's no need to include it. So we just put 2, close bracket. Then we're going to put the plus as it needs to be because this one has been moved over here. We're going to do open bracket, 2. And since the multiplication has also been moved out, we don't put the multiplication. then we do 5, close bracket. Now here we put the multiplication and then we put the place. And then last, we then remove all of the brackets to then get 3, 2 plus 2, 5 multiplication plus. If you want to double check that this will give you the same answer as this, well, all you have to do is same as this did previously. This will give you 5. This will give you 10. And then this will give you 15. 3 plus 2 will give you 5. 2 times 5 will give you 10. 5 plus 10 is 15. So yes, they give the exact same answer. Now we're going to move on to this one over here. Exact same thing we're going to do, starting from the right-hand side. I'm going to find the very first operator. I'm going to move it out of the way. We're going to move down to the next operator. I'm going to move this out of the bracket so it replaces the division over here. So then we're left with open bracket, 2, 5, close bracket, plus 6 division. And then we just remove all the brackets, 2, 5, plus 6 division. Nice and easy. Now, we're going to do this one, exact same thing, starting from the right-hand side. Find the first operator, move it out of the way. Then you head down till you find the next operator, take that, move it out of the way. We're left with 8, 2, 5, multiplication, plus, remove the brackets, 8, 2, 5, multiplication, plus. Now be careful that you don't accidentally mix the order of the operators up when you're writing them out, because you could accidentally put 8, 2, 5 plus multiplication. Now this will give you a completely different answer. This one here, the correct one, gives you 10 plus 8, which will give you 18. This one gives you 7 multiplied by 8, which gives you 56. As you can see, two very different answers, but we want this one over here. And now this one. This one is slightly harder. I'm going to give you guys a 10-second head start if you want to try it out. Starting from the right-hand side, we're going to move over here, take the operator, move it out, move over, find the operator, move it out, move over, find the operator, move this one out. And we rewrite it without the brackets. We get 9, 4, 2, plus 2, multiplied, negative. And that's it for converting infix to postfix. It's as easy as that. If you want to look at how to convert postfix back to infix, we'll be covering that in detail in the Bridge the Gap course. So please do be sure to join in on that. So now we're going to be looking at binary. The definition of binary is that it is a base 2 numeral system that only uses 2 digits. What are these 2 digits? Well, they're just ones and zeros. And each digit is called a bit. A byte is made up of 8 bits. And if you take a nibble out of that byte, you're left with 4 bits. So now we're going to be looking at converting denary to binary. But what is denary? Denary is just your basic numbers, such as 1 or 10 or 15. That's what denary is. It's sometimes also called decimal in computer science, and the denary and decimal are used interchangeably, so don't get confused if you see either one of them. So the first thing we're going to do, we're going to look at this left binary over here. What we're going to do is we're going to look at the rightmost bit, so this one over here. We're going to assign this bit a value of 1. Now, I'm going to explain in a little bit why this is. Just bear with me for a second. What we're going to do now is we're going to move down, moving leftwards through the bits, and we're going to double the value of the bits every time. So 1. Double 1 is 2. Double 2 is 4. Double 4 is 8, 16, 32, 64, and 128. Now you can see I lined them up. That's because those values correspond to these bits. So why is this the case? Why am I doubling it? Well, that's because in computer science, when we are starting from the beginning of something, for example, the beginning of a list, or in this case, the rightmost bit, we label that the 0th item, whatever it is. So this one here will be the 0th bit. It wouldn't be the first, it would be the zeroth, because us computer scientists, we're just weird like that. We don't want to conform to conventions and everything. So that means the second one would be considered the first bit, and then the second bit, so on and so forth. Now, why is this significant? Well, that's because since binary is a base 2 numeral system, and as you probably know from maths, base 2 basically means 2 is the base, and anything will be, that'll be raised to the power of that will be the exponent. So when you're starting at the rightmost bit, the zeroth bit, it will have a value of 2 to the power of 0, which in other words is 1. And then the next one over will have, since it's the first bit, it would have 2 to the power of 1. That'll be its value, which 2 to the power of 1 is just 2. Then the second bit, 2 to the power of 2 is 4, all the way till the seventh bit, which 2 to the power of 7 is 128. So now we're actually going to look at converting it. Now that you understand this, we'll be looking at converting it. So all we have to do here is just add up the values. It's as simple as that. Once we line up the values to the bits, all we have to do is add up the corresponding values. So in this case, all of these, if they are 0, that means they have no value. If they have 1, that means they have the value of whatever that bit has value of. So in this case, it'll be 16 plus 4 plus 2, which is just 22. Nice and simple. Now we're going to move on to this one here. We're going to do the exact same thing. Remember, it's base 2, so it's going to be 2 to the power of 2 to the power of 0, 1, 2 to the power of 1, 2, 2 to the power of 2, 4, etc., etc. Now that we've written all them out, all we have to do is add them up. 32 plus 16 plus 2 plus 1. That gives you 32 plus 16, that's 48, plus 2, 50, plus 1, 51. Nice and easy. Now we're going to look at converting denary to binary. We looked at converting binary to denary, now we're looking at converting denary to binary. So the first thing we're going to do is we're going to write out our values, starting from 1, 1, 2, 4, 8, 16, 32, 64, 128. Now you'll see why in just a second, but this will make our lives easier. Now all we have to do is see which one of these, which one of these goes into 13. Well, clearly 128, 64, 32, and 16 are all too big. None of those goes into 13. So we can just assign all of those a value of 0, since they don't contribute to this in any way. But since 8 goes into 13 exactly once, we write 1 underneath the 8. And then we do 13 take away 8, which is just 5. And you write the remainder, which is 5, up here. And then we do how many times 4 fits into 5? Exactly once. So we do 4 plus 5. Sorry, no, 5 take away 4, which is just 1. And we got 1 remaining. 2 does not fit into 1. So we lose 0 there. 1 does fit into 1 and has no remainders. So 1 there. So the final answer would be 0, 0, 0, 0, 1, 1, 0, 1. However, you see there are 4 zeros and they have no value whatsoever. So there's no point in actually keeping them. So we can just go on and get rid of them. But we need to be careful. If the exam question asks us to give it as a byte, we need to make sure we include all 8 bits. If we don't, then we do run the risk of losing the marks. So be careful to read the question. So now we're going to be doing 42. It's going to be the exact same thing. We're going to label out our numbers first. Just very quickly. I'm going to see 128 and 64, too big. So straight away, zeros for those. 32 does go into 43, exactly once. We get 11 left over. 16 is not big enough. 0. 8 is big enough. We get left with 3. 4 is not big enough. And 3 goes into 2. Well, 2 goes into 3, sorry. And then we got 1 remainder. 1 goes into 1, quite obviously. And there's our answer. And we can just get rid of the additional zeros over here. 1, 0, 1, 0, 1, 1. Nice and simple. Now we're going to be looking what hexadecimal is. Binary was a base 2 numeral system, whereas hexadecimal is a base 16 numerical system. And this uses 16 distinct symbols. What does this mean exactly? Well, you see this table here where you can see the denary on the left and the hexadecimal's values on the right. This will make more sense in a minute when I show you how to convert denary to hexadecimal. But just know that from 0 to 9 in denary is the exact same in hexadecimal 0 to 9. But from 10 to 15 in denary, for hexadecimal, that'll be A to F. We'll be covering why this is the case in more detail in the Bridge the Gap course. This table is here on the right for our convenience, but now we'll be converting 18 to hexadecimal. The first thing we need to do is convert it to binary first. So we're going to quickly write our numbers again. 128, 64, 32, 16, 8, 4, 2, and 1. I'm going to convert this into binary. Goes once there, 0 there, 0 there, once there, 0 there. We could put the zeros there, but again, as I said previously, no need. And now what we need to do is split this into two nibbles. And if you remember, a nibble is half a byte, so it's 4 bits. So we're going to split this into the middle. And the next thing we're going to do is we're going to get rid of these numbers up here and replace them with 1, 2, 4, and 8. Why? That's because we're looking at the individual nibbles now. We're not looking at as a byte as a whole. We're looking at as individual nibbles. So over here, the value, this is the 0th bit in the nibble, and same as here, the 0th bit in the nibble. So there's no need to carry on from the 3rd bit over here into the 4th bit. We just start again, 0th bit from here. And now what we do is we convert these individual nibbles into their denary values. The left bit nibble here, this denary value is just simple, 1. This one over here is just simple, 2. Now we're going to move over to the table here, and we're going to see denary 1 and 2, exact same in hexadecimal, 1 and 2. So we're going to come over here, and the hexadecimal of the denary number 18 is just 1, 2. Now be careful not to say 12, because it's not 12. It's two separate symbols, 1 and 2. We're going to do the same with 60 over here. Now, let's look at our learning objectives quickly again to see what we've learned. We've successfully learned what postfix and RPN are, along with what infix is. We learned how to convert infix to postfix. We learned what binary is. We learned how to convert denary to binary. We've learned what hexadecimal is, and we can now convert denary to hexadecimal. So, with that being said, thank you for joining us today. We have quite a few people with us today. What's that? About 11, 12 people. That's actually quite a few people into this webinar. And I'd like to thank you all for joining us today. If you'd like to contact us, our email is the 3tutors@gmail.com. If you'd like to contact us on our socials or just check them out, we're on Instagram and TikTok at the 3tutors. The link to our website's right here on the screen if you'd like to access that and find out any more information. With that being said, I thank you all for joining us and hope you have a good day.